Okay, students, let's do our universal gravitation problem. We're trying to find the force of gravity between the moon and the earth. So the first thing that we're going to do is we're going to list all the information. So m1 will be the mass of the earth, so 5.97 times 10 to the 24 kilograms. Mass 2 we will use for the mass of the moon, 7.35 times 10 to the 22nd kilograms. And the distance that separates them is 3.84 times 10 to the 8 meters. Now, it is important to note that when we're talking about distances between objects when we're dealing with gravity, if this is Earth right here, there's the center of Earth, and the moon is here, and there's the center of the moon, the distance is always towards the center, or to the center. We always will use universal gravitational constant, big G, 6.67 times 10 to the minus 11 Newton times meter squared divided by kilogram squared. And in this problem, we're asked to find what is the force of gravity between these two objects. Let me rewrite that. So our equation for universal gravitation, Fg equals, we've got big G, m1, m2 divided by distance squared. So that's the equation that we're going to use. Now you can use a calculator to help, but we do need to have it set up correctly. So let's put all the numbers in first. So we've got our 6.67 times 10 to the minus 11 Newton times meter squared divided by kilograms squared, universal constant. Mass 1 was the Earth, 5.97 times 10 to the 24 kilograms. And the mass of the moon, 7.35 times 10 to the 22nd kilograms. All of this divided by the distance squared, 3.84 times 10 to the 8 meters, and we have to square that, right? And that's what our force of gravity will be equal to. So from here, we have a scientific notation problem. So we're going to multiply on the top, so we'll multiply all the bases. We'll write our times 10, and then because we're multiplying, we'll add all the exponents. We can also do downstairs in the denominator, we have a power raised to a power, so I'll distribute that outside exponent to the base, so I have to square my 3.84. I'll write my times 10, and because I have a power raised to a power, I need to multiply my exponents. Okay, so now Fg equals, when I multiply all those together, I get 292.7 times 10 to the 35 divided by, when I square that, I get 14.7 times 10 to the 16. And now I have a division problem. So this will give me, let's see, 292.7. I have to divide it by the other base. Then I write my times 10, and because I'm dividing, I need to subtract my exponents. So this division will give me 19.9 times 10 to the 19. Now this is not the right format. I need to have one digit and then the decimal. So this will be 1.99. Because I'm making my base smaller, I have to make my exponent bigger. And then of course the unit is newtons. So 1.99 times 10 to the 20 newtons is the force between the moon and gravity when they're this far apart, 3.84 times 10 to the 8 meters. You can do these using a calculator. If you do use a calculator, you still would have to show me the equation. You would have to set up this line here that shows the numbers with the units, and I also want you to set up this line here so I know that you know how to do scientific notation. And then you can put all the numbers into the calculator to make it a little bit easier for you. There's also an option where this is solved for force here, but we may also, let me get rid of that, we also may need to solve for mass. And if we solve for mass, a little bit of algebra will rearrange this. M1 equals force of gravity times our distance divided by big G, the universal constant, in m2. m1 and m2 are interchangeable in this case. You may also have another problem where you have to solve for the distance, and this one gets a little bit trickier because we'll have a square root. If I rearrange our universal gravitation equation and I solve it for distance, I end up with big G, m1, m2 divided by our force of gravity. But because up here in our equation this is d squared, I need to take the square root of all of this. Your calculator will have no problem doing that, but if you do this out using the steps of scientific notation, we'll run into a problem. The workaround for this is that I can rewrite this, big G, m1, m2 divided by our force of gravity. The way that I can write the radical or the square root is I can make it to the 1/2 power. And if I do that, now I can use my rules that I did over here when I have a power to a power. I can just simply multiply whatever I have here by 1/2. The only other trick that you'll run into is you want to make sure that the inside exponent is even. So you'll have to make an adjustment with the base if your exponent is odd, so that you don't end up with a fraction for your exponent. So here's a couple examples of how we do the universal gravitational problem, and I will see you in class.